Yeah. So let us start this particular session. Before going to start this particular session, in our previous session, we have started with discussion of what is the difference between ASIC and what do you mean by FPGA, and where do you find your ASIC chips and where do you find your FPGA chips, and what is the exact difference between your ASIC and FPGA in terms of architecture we have seen, and some of the examples we have seen for FPGA, and some of the examples we have seen for ASICs, right? So yesterday's session, is it clear? Any doubts or any queries? And also we have uploaded the recordings also. You can watch the recordings. Okay. So any queries or any doubts? Shall we move with today's session? Okay, great. So I think we are good to move. Yeah. Now, so in our day two of FPGA design, this particular course, what are we going to do is we are going to first of all see the ASIC design flow. Okay, let us going to let we will see one example. Like we will see one particular design, and for this particular design, we will see how to perform a ASIC design flow. What is the ASIC design flow we are going to do for a particular design? Okay, instead of just seeing the steps, we are going to take one example, and with this example we will see. Okay, now what is this design, sir? Is it's a simple design. We need to design a UART controller ASIC for a microcontroller SoC. Now before that, I need to Rahul, are you there in the group, in WhatsApp or Telegram group? There are two groups actually. One is WhatsApp and another is Telegram. Are you present in any of that particular groups? So can anyone tell me what do you mean by a UART? Full form of UART, anyone knows? Okay, so Universal Asynchronous Receiver Transmitter. Okay, sender and receiver transmitter. Now, where do we find this UART? Like, what is the need of this particular UART? Yes, Universal Asynchronous Receiver Transmitter, exactly. Now, where we actually use this UART? Serial communication, exactly. Okay, to transfer the data for the communication, exactly. Okay. Now, is this particular UART, is it a software or is it a hardware? Exactly. So UART is basically a hardware. Okay. So what is going to happen is, let's say this is your chip, and you are going to have a UART IC present over here. Okay. Let's assume we have a UART IC which is present over here. Normally, UART will have two lines, RX and TX. We are not going to discuss in detail about what is mean by this RX and what do you mean by TX and how it is going to follow that particular thing. Already this playlist is already available in our channel. You can refer that. Okay. Now it is an asynchronous protocol. We are not going to have any clock pin, right? Now this is an IC, right? Now if we want to control this particular IC, and if we want to control this particular IC, we are going to program our FPGA. Okay, this is our FPGA, and FPGA is connected to our UART IC. Okay, let's say we are discussing about ASIC design flow, right? So let's say we are going to have an ASIC chip, and this ASIC chip is going to control this IC, whether to transmit or whether to perform the receiving operation or how to set the baud rate. Like that, we will have different factors, right? So that particular factors are being decided by this particular ASIC chip. So this ASIC chip is going to control this particular UART IC chip. Okay, this is my UART IC. Okay. So normally 1650 like that, you will have some particular chips, right? Now this ASIC is going to control this particular chip. Now we need to design this ASIC, okay, so that it is going to act as a UART controller. And so let us see how we are going to design that. So first one is specification. Now, what is this ASIC chip is going to do? That is what we are going to specify. Okay. We are, and please remember, we are not designing this IC. Okay. This IC is already designed. What we are going to design is we are going to design a ASIC chip which is going to control this UART. Okay, so this is going to act as a controller. Okay, this ASIC chip is nothing but a UART controller. Okay, now what is the specification? The chip must set the baud rate to 115200, and it need to have the data format of 8 data bits, no parity, and one stop bit. See, your IC chip is not going to send or send the data frame, or it is not going to set the parity bits. There should be some controller who is going to create the frame or filter the frame, right? So that is what we are going to do. The specification is we need to set the baud rate to 115200, and data formats is 8 data bits, no parity, and one stop bit. And if you are a person who don't know anything about your protocol, who don't know anything about baud rate, please don't worry. Just see this as a specification. Some specification you have got. Okay. Just you are reading that particular specification. That's it. Is it clear for everyone who don't know about your protocol? Is it okay? So don't worry about that particular thing. Just read it as a specification you have got. That's it. It is in some. It is some just random specification you have got. You are reading that particular random specification. You don't know anything about that. Okay. Is it clear for everyone? So those who don't know about this UART protocol, is it okay? Yeah. Now, yeah, great. Now, so we also have an interface APB bus from the CPU. Okay. So this ASIC chip and this UART are basically connected with an interface which is known as APB interface. Now, what do you mean by this APB interface? This is also presented on our channel. Okay, you can watch it over here. The recordings are already present. The APB interface, using this APB interface, the ASIC chip and the UART chip are connected. Okay. Now, the clock should be of 50 megahertz and power and area targets are defined. So at this stage, at this first step, which is nothing but our specification, we are not going to code anything. Just we are going to see the specifications. Like if you are going to buy a car or a mobile phone or something, right? Any electronic gadget, if you are going to buy, you are just going to read the specifications. That's it. So is it clear? The first step, is it clear? Yeah, we are not going to see about the specifications and all. Yeah, start bit is also there, but here in the PPT it is missing. Okay, start bit, data bit, parity bit, and stop bit. Okay, great. So this is the first step. So in the ASIC design flow, the very first step is nothing but our specification. Okay. So in the ASIC design flow, we are going to have the very first step as our specification. Now, what is our next step? Let us see what is the next step. So this is our some chip we need to design. This is a controller which is going to control your ASIC. Sorry, which is going to control your UART. Okay. Now, next is architectural design. So in this architectural design, what we are going to do is we are going to design a UARTX block, RX block, baud rate generator, control and status register, APB interface logic. So this is how we are going to build. Let's say this is our chip UART controller. So in the specification, we have seen just a box. Okay, it is nothing but our UART controller. Now we need to design the architecture. Architecture in the sense, if we are building a particular a house or something, we are not going to build a simple hall, right? We are going to see what should be present inside that particular thing. Okay. So here also in our UART controller, we are going to plan what are all the blocks or what are all the modules which should be present inside this UART controller. That will come under your architectural design. So what I'm going to build is nothing but a UART TX block, UART RX block. This block or this module is used for transmitting the data, and this block is used for receiving the data, and another block which I'm going to design for baud rate generator, and one more block is for controlling and status register, and another is APB interface logic. Okay, because this particular UART controller needs to communicate with your UART using your APB interface. That particular logic I'm going to design. So like this, in the architectural design, I'm basically designing what are all the blocks, or I'm deciding what are all the blocks which should be present inside this particular controller. This is nothing but my architectural design. Is it clear? Where is the block diagram? We have APB and UART as we mentioned. Okay. So first of all, tell me the step two. Is it clear? APP is just an interface means we need a specific protocol and code for its implementation. Yeah, we'll come to that particular point. The conversion from UART to APP is not clear at architecture level. Okay, I will come to that particular points. Okay. So let's say I will take the example of your FPGA only. Okay. Uh, we are going to learn this FPGA, right? Zinc FPGA. Okay. So generally, this Zinc FPGA is going to have AXI interface. AXI interface. Now, what do I mean by Zinc FPGA having AXI interface? Is nothing but this Zinc FPGA is going to have AXI signals. Okay. Now, if I want to establish the connection between this chip and a peripheral chip like a UART controller or something, which is basically controlling my external device like a UART. Okay. Let's say this is nothing but a UART controller. Okay. This is very low bandwidth and low speed because it's a peripheral device. It is controlling a peripheral device. It cannot be very high speed, right? So it is very low speed. So for basically for low speed devices, we will use APB interface. Okay, that means APB related signals which we are going to use. Okay, now so this APB interface, using this APB interface or APB signals, we are this UART controller is going to have. Okay, UART controller is going to have this APB interface signals, and this FPGA is going to have AXA signals. We will have something known as bridge. This bridge is going to basically convert this AXA signals into APB signals. Okay, and this UART controller, after receiving the commands from this chip, your FPGA or ASIC from this bridge, this UART controller is going to convert that particular signals or transactions into UART signals. Like for UART, we will have RX and TX, right? So it is going to convert this commands which it has received from the FPGA or ASIC from using the APB interface. It is going to convert them into UART related signals. That is the process it is going to happen. Is it clear? If possible, we will discuss this particular example using the Vivado. I will show you the block diagram how it is going to look like. I think it is clear, right? So this ASIC is going to have your AXI signals associated with it, and UART controller is going to have, this is your UART controller is going to have APB signals associated with it. This is nothing but APB signals. And for converting AXI to APB, you will have one bridge. The bridge will convert AXI to APB. Okay. And after this UART controller have received the signals from ASIC, okay, that is using this AXI, the bridge will convert them into APB. And after receiving those commands or the data, it is going to convert them into UART interface. It is going to convert them into RX and it is going to convert them into TX. It is going to give it to the UART physical chip. This is the conversion process it is going to follow. Now is it clear? I could not follow it completely. We also have EXIS out then URTB. I think now with this example, with this diagram, it is clear, right? Yes. Yeah, that is what I'm saying, right? There is a bridge which is present in between. Mm. Rahul, yeah. AXI is from CPU, exactly. Yeah, yes, Rahul. I am not thinking of going into this particular deep concepts because there are a lot of freshers also. But just try to understand there are few signals. Okay. Okay. I will take one more example. Let's say if I'm trying to speak in Hindi. So some people may understand, some people not may understand, right? So that is the same thing it is going to happen. ASIC is going to have one particular protocol. It is going to have some signals, AXA signals present with it. And your controller is going to have some set of signals which is present. Okay. Let's say if the user wants to send a data FF from the CPU to our UART. Okay. So this data, first of all, it will be sent through this AXI to the bridge, and this bridge will convert it into APB format, and from this APB format it is going to convert it into UART format. So this is how the process is going to happen. Now is it clear? If it is not clear also, no problem. This is not our agenda. Our agenda is just to understand the architecture design. In the architecture design, we are going to have TX block, RX block, baud rate generator, control and status register, APB interface logic. We are not discussing about UART controller with APB interface. That course we are not discussing. That we will discuss in the future. Okay. Further, the requirements and the prerequisites are different. Okay. Okay. Yeah. Okay. So that is what our main agenda will be. Like you will be learning the protocols, but you don't know like where you are actually using them. Okay. We will try to explore them also. But for that we need the protocol knowledge also. So that's why I'm skipping that. Okay. Yeah. Okay. Now, next, the second step is basically architectural design. And I have received one more question also, like someone I haven't noticed that. 1 minute, let me see that. So, second step is architectural design. Let me see the second question I have received. Where is it? APB is just an interface, means we need a specific protocol and code for its implementation. Yes, we need APB interface code also. Okay. So that process, like we are going to have a top module, and in that particular top module, we are going to instantiate the our actual UART controller design. Okay, is it clear? Yeah. So the second step is architectural design. Okay. Now the next after the next architectural design, we are going to have something known as RTL design. Okay. So in RTL design, we are going to use either Verilog or VHDL. Now, why we are using this Verilog and VHDL languages is using these languages, we are going to develop these blocks. What are these blocks? Your TX block functionality we are going to design. Your RX block we are going to design. Baud rate generator we are going to design. Control and status register we are going to design. And APB interface logic we are going to design. Okay. So this particular blocks we are going to design, and how we are going to design and what is the logic which is present, that is not scope of this particular discussion. That is not the scope of this particular sessions. Okay. So using these languages, we are going to develop. Okay. Is it clear? The third step, is it clear? I think most of you have worked with Verilog language, right? So this is the third step, RTL design. So difference between Verilog and system Verilog. Verilog is basically used for designing. System Verilog is also used for design. Nowadays, people are using system Verilog for designing. And coming to system Verilog, it is useful when you are developing your test benches, when you are verifying your design like your SOC, there your system Verilog will be very helpful. Okay. Okay. Uh, okay. So let's say if I'm going to have a simple processor. Okay. Now, can anyone tell me what are the specifications of your phone processor? Like what are the specifications of your phone processor with having with you? Any idea? Exactly. So we are going to have some clock speed and what to say. We will have different specifications. That is nothing but your first step. That is nothing but my specification. Now, in the layman terms, if I want to discuss the architecture, so in my processor, I'm going to have ALU, okay, and control register, and I'm going to have set of registers, okay, depending upon the architecture you are going to have, and different type of blocks I'm going to have, right? That is nothing but my architectural design. Now is it clear, Rahul? Okay, same like your processor where you are going to have different type of blocks like ALU, register. If you have worked with that particular simple processor design where you are going to have ALU, registers, control register, and different type of blocks. Here also, in case of your UART, it's some architecture. I've just given some architecture. That is what I'm saying. Please don't go into what is this TX block, what is this RX block. This is not the scope of this particular session. We will have another sessions planned for this particular IP development. Okay, yeah, we will move forward. Now, next comes the functional verification. Okay. Now, in the case of your functional verification, you are going to write the test bench. You are going to check if your RTL code which you have written is working as you have expected or not. For example, you have designed a UART IP, UART controller IP, and if you are basically writing a test bench and you are sending a particular transactions and you are going to receive them and you are going to check whether the data which you have sent whether you are able to receive it or not. Okay, so this is nothing but my functional verification. Okay, so we are going to use the APB interface for sending the data to the UART, and we are going to use the APB interface for receiving the data. Okay, so if let's say if we are not satisfied with the result, or if we are not satisfied with the results which we are expecting, which we need to get. Okay, again we are going into the RTL design and we are going to add or delete, or we are going to modify our Verilog code. Okay, so is the fourth step clear? So that is nothing but my first step, second step, and third and fourth. Okay, so before that, as I've said you, so if you want to perform the Verilog code and if you want to perform the functional verification, these are the tools which we can use. First one is Model Sim, QuestaSim, VCS Synopsys, Xilium, and this is Icarus and Verilator also you can use. So these are the available tools which you can which you can write the Verilog code and you can perform the functional verification. Okay, yeah. If you want, you can note this particular tools. Now, how to use these tools, and this is not we are going to discuss, but these are the available tools which you can explore. Okay, yeah. And for synthesis, that means if we want to convert our code into synthesizable code or gate level netlist, we can use this Vivado Xilinx, or if we are working with Intel based FPGAs, you can use Quartus Prime, Synopsys Design Compiler, Genus, and Uses. Okay, so these are the tools which we can use for synthesis. Now, can anyone tell me what do you mean by synthesis? What do you mean by synthesis? Can anyone tell me? Exactly. So converting RTL code into gate level netlist so that it can be implemented on your physical chip, right? Okay. Yeah. Now, so another is logical synthesis. That is what we have said. These are the tools which are used for logical synthesis. So basically, it is nothing but converting your RTL code into one of the gate level netlist, and according to the technology library you are going to use. Okay. Now, so this is about your front end. Now, next comes the back end. Back end, we have physical design like floor planning, placement, clock tree synthesis, and routing. And we have something known as static timing analysis. After this FPGA design course, we are going to have the discussion about this static timing analysis only. Okay. And if you want to learn this physical design in more deep, like what do you mean by floor planning, placement, clock tree synthesis, you can explore our channel. Already one course is happening in parallel, and physical verification is also happening there. And after this, we are going to have tape out where the final design is sent to the foundry, and we are going to have the fabrication and testing. So this is how you are going to basically have from the specification to the architectural design and the RTL design, and coming to the gate level netlist conversion and doing physical design, static timing analysis, physical verification, and the static timing analysis can also be used in after writing your Verilog code. Okay, after this particular step, also you can use your static timing analysis. Let me write down here. You can include your STA over here. Okay, so this is how you are going to perform this. Uh, this is how you are going to perform your ASIC design flow. So I hope this example is little bit easier to understand. First of all, tell me, is this example clear for ASIC design flow, or is it not clear? So if it is not clear, let I will go one step below and I will take one more example and I will explain that. Because everyone will explain the processor, or we learn simple examples or of adder or subtractor or something. I wanted to give one real time IP example so that you might get some understanding of how the things work. Please respond in the chat box. Is this example clear? Uh, is it easy to understand, or should we take one better or easier example than this for ASIC design flow? Okay, clear. One more example. Oh, okay, okay. I can see mixed reactions. Okay, okay. Okay. Normally, we study about simple ASIC design flow. So I wanted to have this with one real time IP example so that the things will be clear. Okay. Okay. No issue. And I'm getting few responses out of 40. What about remaining people? You're generalizing. Like for example, we are just considering the example of a simple IP. So for this particular IP, we are performing the functional verification. In the sense, we are basically checking the functionality of this particular thing. Like if you want to verify entire functionality of your SOC or multiple subsystem, then it's a different concept. Like we will use the languages like SV for developing the test benches, and we are going to write multiple test cases. Okay. Yeah. And what about remaining people? Yeah. I hope I haven't taken a complex example. Okay. Okay, no issue. We will take one more simpler example. Like we will take one example of an ALU. Okay. And we will try to understand the ASIC design flow. No issue. Okay. Yeah. So I think we will wrap up this session over here, and we will take one simple ALU, sorry, simple processor example, 8-bit processor example. So I recommend you to once go through how a 8-bit processor is going to look like, and what are the components which are present in that particular 8-bit processor. Okay, so that you can able to in sync with me. So whoever are facing the issue understanding this particular UART IP protocol, UART IP ASIC design flow, once please look into the 8-bit processor design, like what are the blocks which we are going to have, so that the things will be clear. Okay. Yeah. So that's all about this particular session. If you have any doubts or any other queries, you can stay and discuss with me, or else you can leave the session. Okay. Thank you. What was done in the first session, as today we seem to have so many blocks or protocol? Nothing has happened. First session was an introduction, and today why you are going to see this many type of blocks or protocols is nothing but for a case study. It's just a case study to understand how actually the things work. That's it. Sure. I totally understand. We will take one a simple 8-bit processor, and we will try to understand it. No worries. We will discuss it again. Yeah. Other queries? Anyone wanted to discuss any other queries? Shall we end this meet?